Okay, thank you, Justin, for that introduction. It's really good to be back here at Langley, where I was actually a NSTRF fellow during my PhD with Dr. Bob Moses, who is actually in the audience. So it's great to be back. As is mentioned, I'm a fairly new assistant professor at the University of Colorado Boulder, so I've been there since 2022. And today's talk is about hypersonics, planetary reentry, and the role of our research laboratory, the University of Colorado Magnetoaerodynamics and Aerospace Plasmas Laboratory. And hopefully by the end of today's talk, you'll have some insight into what we do and what that means. Okay. So I wanted to talk a little bit about my career motivation and background. Why this lab? Why now? Historically, I've always been inspired by the challenges of human spaceflight. And when I went to the University of Alabama in Tuscaloosa as an undergraduate student, we really were focused on engineering mechanics. And so I did a lot of materials work, which led me down the path of 3D printing and in situ resource utilization in space using additive manufacturing. And this was around the time when I was doing my first internship at Marshall that NASA had launched the NASA Space Technology Research Fellowship Program, which is now known as NSTGRO. And so I applied to do ISRU in space through additive manufacturing and was selected for that award. Upon going to graduate school, I really realized that I wanted to do more hypersonics, more reentry. And so that is where this idea of tapping into some work that had been done at Langley in the past on regenerative air braking came to the forefront. So could we use the entry plasma generated during hypersonic entry to achieve some useful aim? Could we harvest energy resources with it? And so that's mostly what I did for graduate school. After graduate school and a brief stint as a research faculty member at Georgia Tech, I went to the Aerospace Corporation, switched fields, went to the astrodynamics department, and had a chance to see sort of the national security space side of things. So did cislunar space, low Earth orbit, various things for that department, but also kind of served as the hypersonics liaison and realized that, in our department, although we interfaced a lot with those groups, we didn't necessarily have that expertise in-house. And so that was something that I did for them and still do today. And so kind of a highlight was really finding power in interdisciplinary work and trying to build collaborations and partnerships and work across disciplinary boundaries to achieve new innovations. So that was kind of why I like doing what I did and why I continue to do what I do now. And so the original motivation for the work was joining my advisor's PhD research group at Georgia Tech. And there, the focus was on entry, descent, and landing, and a lot of the expertise was specifically for Mars. And so reentry at Mars to date is an example of a hypersonic flight regime. So we're going far greater than Mach 5. And it's a challenge. It's an engineering challenge because we have to reduce our relative velocity to the planet by so much in so little time. And so Mars is a particular challenge, or had been a particular challenge, because we have a thin atmosphere and we use drag to do this deceleration. And because of that, and for physics reasons, we couldn't really land using current technology things much larger than the current rovers. And if we have aspirations for things like a human mission to Mars, obviously we would need to improve that technology. And so through my NSTRF fellowship in collaboration with Langley, we kind of tried to make the argument that magnetohydrodynamics could be one such technology that can enhance entry system readiness for things like landing at Mars or air capture at the outer planets and things of that nature. So that work was really the motivation, I think, for kind of starting this lab. And so it was studied in NSTRF 13 award at Georgia Tech, at Langley and JPL. And that was actually followed up by a sponsored research project awarded from Langley to Georgia Tech so that I could complete my dissertation work there. So this word magnetoaerodynamics, what does it really mean? So magnetoaerodynamics is magnetohydrodynamics for aerospace plasmas. So it's really just a naming convention in which we're going to say that we're going to apply the study of electrically conducting fluids to the problem of hypersonic entry plasma specifically, which presents a different use case than the classical application of magnetohydrodynamics. So magnetohydrodynamics has been around for a long time. One kind of famous example is introduction of magnetohydrodynamic waves by Hannes Alfvén. And that was kind of studying the magnetosphere. And one of the assumptions there is that you have infinite conductivity. It's a collisionless plasma. Well, that's not the case for a hypersonic entry plasma. We have a lot of neutrals bouncing around, and it's actually non-ideal MHD. And so magnetoaerodynamics is a little bit different, I think, from magnetohydrodynamics, if not in principle, then certainly in application. So magnetoaerodynamics is truly an interdisciplinary endeavor. It involves aerodynamics, electromagnetics, chemistry, and thermodynamics. And why would you consider it for reentry? Well, during hypersonic entry, we have a plasma that's created from thermal ionization, and it could potentially enable several useful benefits. So when you're driving in a hybrid vehicle and you slow down and you charge the battery, that's regenerative braking. Well, you can actually do regenerative aerobraking. A similar mechanism, the kinetic energy of the vehicle is translated into thermal energy, which gets backfed into electrical energy stored on board the vehicle. And at the same time that we're generating energy, we must be slowing the vehicle down. So now we have a deceleration mechanism. And you can imagine that if we had such a deceleration mechanism, perhaps mounted to a gimbal or in different axes, now we have control. In addition, the way that this mechanism works is it actually pushes the shock wave a little bit away from the surface of the vehicle, which reduces your convective heat flux. In fact, you can actually do this analysis for the magnetosphere around Earth. And if you look at the jump conditions that form the shock, there's a shock that's created between the solar wind and the Earth's magnetosphere. And that shock is created not necessarily by fluid dynamic pressure because we're in the vacuum of space, but magnetic pressure. And you can solve for the Rankine-Hugoniot jump conditions, you can obtain a shock front. And you'll find that the distance that shock is separated from the Earth is related to the magnetic pressure, just like it is for fluid dynamic pressure. And the interesting consequence of that is now we have a mechanism to potentially reduce heat flux on sharp surfaces. So there's a lot of benefits to reentry systems, and I think hypersonic systems in general, that is possible if you can do the work necessary to advance the technology. So our lab, we abbreviate as CU Map Lab for short. We focus really on a range of topics in our lab. So to date, we focused on hypersonic trajectories. We've been building a large experimental facility. We also are developing some new diagnostics, so aerothermal diagnostics, but also plasma diagnostics, and of course, magnetoaerodynamics. So currently, our group has 6 PhD students. And then as of fall 2024, we will have 8 PhD students, taking into account 3 incoming and 1 who's graduated, and myself. And so from left to right, their names are Danny Wen, Tomas Remick, Jay Flores Gouveia, Kevin Bonnet, Ethan Leong, and Stephen Latimer. And these students are really what makes the lab go. And so I really enjoy working with them, and they've contributed heavily to our progress up to this point. So when I say the word plasma, I think what comes to mind, of course, is a fourth state of matter and some type of glowing substance. But in terms of what makes a plasma different, a plasma is not necessarily only an ionized gas, right? Because in a gas, particles can interact in one of 2 ways. They can collide with each other, or they can collide with a container. And those interactions, those collisions actually give rise to all of the gas dynamic properties that we observe. Well, what's different about plasmas is because we have free electrical charges, we now have an electrically conductive gas. And what that means is that now these molecules, these particles, can actually experience interactions due to fields that are, produced at a distance. So normally for fluids, we would have gravitational fields that work on the fluid or act as a body force. But now we've added a new body force, the Lorentz force interaction. And this arises fundamentally due to 2 different electromagnetic forces. So there's the electrostatic and the electromagnetic interaction. So electrostatic interaction is just opposite charges attract. And then there's the electromagnetic interaction, which is the forces that a charged particle would experience due to motion through a magnetic field. And so now we have a gas that we can manipulate with body forces that are not gravity only. And that's really what's different about a plasma, is that you have all these new dynamics that are added. It also makes it difficult to simulate as well. So although plasmas are sort of not common in our daily lives, in our interactions, they're actually the most common element in the universe, and they are the state of matter that experiences the widest range of properties, so temperature specifically. And so there are many different types of plasmas. So CFL bulbs are kind of being or have been phased out, but a compact fluorescent light bulb is an example of a plasma discharge that produces light at low power. But you also have very high energy plasmas, so solar plasmas, so high temperature plasmas. And then you can have plasmas that are produced for other purposes at very low densities, like electropropulsion plasmas. So this is a Hall thruster type plasma. And the plasma that we're going to be talking about is a reentry plasma. And in this talk, I used to have kind of an artist rendering of what such a plasma would look like photographed, but it's kind of interesting. SpaceX, with their Starship reentry, had this camera pointed at the vehicle, and you can actually see this reentry plasma, which is really, really interesting and kind of cool. But it's always been there, right? And so the entry plasma that we're going to be looking at is going to be something in which, yes, there's ionization, but it's really weakly ionized. And it's at a high enough density that we can consider the gas to be a continuum. So it's not in a vacuum, which means that we're going to have a lot of collisions between electrons and ions and those neutral particles. And so that is really the defining characteristic of magnetoaerodynamics and kind of what we're looking at in our lab experimentally, and the reason we need to do that experimental validation. So I also wanted to do a brief introduction into magnetohydrodynamics and sort of the working principles. So on the right, I have this example of something called a Faraday type linear MAC generator, which is probably one of the simpler MAC generator designs you can think of. This design isn't necessarily appropriate for an entry vehicle because it has an open channel through which the plasma must flow, but it's a useful conceptual example for how this interaction works. So just to give you a layout, here from left to right, we kind of have an ionized gas source moving through an open channel. And that open channel, we can think about it conceptually as applying a constant magnetic field flux in a direction that is mutually perpendicular to the motion of the plasma, which you can think of as a current. And what's going to happen is that as that charged particle flux crosses the magnetic field vector, it's going to induce an electric field in a direction that's mutually perpendicular to both of those vectors. And that electric field, if it exists across two electrodes, will drive a current. And if I connect a load across those electrodes, now I can extract electrical energy from this moving plasma. So that is the working principle of a Faraday type MAC generator. So magnetohydrodynamics refers to the study of electrically conducting fluids. So properly speaking, magnetohydrodynamics is not plasma modeling. It is a plasma model in which we are treating the plasma as a fluid, which doesn't necessarily always apply, but we're going to use that model here. And essentially, if we can treat the plasma as an electrically conducting fluid, then we can kind of build off of existing hypersonics code models and add additional fluid species and model the plasma that way, assuming that we keep track of certain other interaction effects as well. And so an MAC generator converts kinetic energy from a moving plasma into electrical energy, but it's really a useful construct for understanding the mechanisms by which we can interact with this plasma that's outside of the vehicle from within the vehicle and not necessarily even have to touch it, which is why it's so interesting for reentry. So how do MHD, reentry, and hypersonics kind of go together? Well, at hypersonic speed, there's this rapid deceleration, subsequent compression, and then heating of the flow behind a shock wave. And we have to heat it tremendously. So for an air plasma, you're looking at temperatures in excess of 5, 6, 7,000 Kelvin. And the reason for that is that in air, oxygen begins to dissociate around 3,000 Kelvin. Nitrogen begins to dissociate around 5,000 Kelvin. And after we fully dissociate the species into their atomic form, so atomic nitrogen and oxygen, then significant ionization really begins. So it has to be hot. And it also has to be high altitude. The other reason for that is that it's not just the temperature, it's the pressure. And if I have free electrons and I want them to remain free, then I must minimize collisions with other particles, because otherwise you'll have recombination. You won't sustain a high electron density. And so during hypersonic entry, particularly direct hypersonic entries, we do have this high Mach number, high altitude, high temperature flow. And an MHC generator, in theory, if it were incorporated within the vehicle, could convert vehicle kinetic energy, otherwise lost as heat, into useful energy, while simultaneously augmenting our aerodynamic lift, drag, or control moments, and helping us with heat flux mitigation. So that seems pretty attractive, and I'm certainly not the first person to notice it. And so the question is, well, how have these effects been studied in the scientific and engineering community to date? And what gaps might exist that still need to be addressed? So I'd like to kind of go back to the beginning for magnetoaerodynamics. So kind of around the dawn of the space age, a similar study, magnetoaerodynamics has been studied alongside the emergence of the space age. And essentially the original purpose and study for magnetoaerodynamics was actually for ballistic missiles, much like a lot of the heritage for human spaceflight technology. And so there were two different individuals, I believe at Cornell, and Ressler and Sears, they published this seminal paper in 1958, and it was called The Prospect for Magnetoaerodynamics. And so I've shown on the left an excerpt of one of their figures for a magnetic field on the forebody of a ballistic missile. And the idea was, could we use this to enhance the deceleration of that missile? And so there was some promise to the idea. Certainly the physics work out. And later on, Zymer and Bush, who was then a PhD student at Caltech, actually did some experiments. So what you're seeing on the right is a shadowgraph image of two spheres. So the one on the left has no embedded magnet, and the one on the right does have an embedded magnet. So you can actually see the shock front being pushed away from the vehicle. But at the time, technology to implement these really large electromagnet on vehicles, as well as potentially the need, right? So there's plenty of atmosphere at Earth if you want to decelerate, maybe didn't merit inclusion of the technology. And it didn't really, go too far after investigation in the 60s, both experimentally and numerically. Also, from a numerical standpoint, it was kind of difficult to develop semi-analytic models that you could really solve that would capture all of these effects. And so with the emergence of modern computing, MHC was sort of picked up again for hypersonics. And so numerical investigation by John Pogge of AFRL, who's now a professor at Purdue, actually compared well to the previous analytical and experimental investigations of the magnetohydrodynamic flow around a sphere. So then one of the things that was enabled by then modern computational power was actually doing this simulation of these MHC effects over an entire entry trajectory at Earth. And so that's what's shown here on the right. So this is the work of Fahino et al. It's in a journal of Spacecraft and Rockets. And they did this study for the OREX reentry vehicle at Earth. And at each point in the trajectory, they actually computed what the effective drag force was, including MHD and non-MHD effects. So the solid line here shows only aerodynamic drag, and then the dashed lines show the additional drag due to MHD effects at various applied magnetic fields. So you have two consequences here. The first is that my peak deceleration is lower. The second is that where that deceleration occurs has changed. It almost looks like a bimodal pulse. And the reason for that is that here in the upper atmosphere, we actually don't have sufficient density to cause a lot of aerodynamic drag. So if we can bleed off more of our drag higher in the atmosphere, that's effectively equivalent to lowering the ballistic coefficient of the vehicle. And that also translates directly to a much, much lower convective heating rate, which is really an interesting result. So, of course, here at NASA Langley, there's been a lot of heritage looking at Mars reentry. And so work done by Bob Moses here at NASA Langley, funded at the time through Langley, performed calculations to determine what would the electrical power available to MHD be for Mars entry. And so that's what's shown here on the bottom left. And then at the same time, Min-Kwan Kim and Ian Boyd. Ian Boyd is now faculty at CU, and Professor Kim is actually now faculty overseas in Europe as part of Europe's MHD investigation. And they performed MHD CFD simulations of the Mars Pathfinder entry forebody with somehow a 1 Tesla magnet embedded in the forebody, and just to see what the effect would be. And what they found was that actually the total potential Lorentz force drag was on the order of the aerodynamic drag. So the dark gray bar is aerodynamic only drag, and then this lighter gray bar, this is the Lorentz force drag. And it's a really interesting result. And it's a little subtle here, and I like to point this out on this chart. The aerodynamic drag component went down when we added the MHD drag. And the reason for that is that we're actually pushing the shock wave away from the vehicle. And although for hypersonic vehicles, we have primarily pressure-induced drag, there is a very small viscous component to that drag that is caused by interaction with the boundary layer. And so you can actually see that go down a little bit in the results, which I always think is kind of interesting. So kind of doing a gap analysis here. Well, previous investigations kind of deploy either analytical approaches or kind of complex numerical simulations. And in either the analytical or numerical simulation approach, this is kind of going to require some advanced knowledge of the vehicle, and it's computationally intensive. Moreover, we don't have enough experiments to really validate these. I can probably count the number of MHD experiments done to date in plasma tunnels. It's less than 10. That are published in the literature. So not a lot that are sort of relevant to reentry. And so there's a need for experimental investigation of MHD interaction for hypersonics. And because of the computational complexity, there's also a need for conceptual design tools or reduced order models, essentially, that we can incorporate into online trajectory optimization tools and actually find, acceptable use cases to target for MHD. So in terms of experimental magnetoaerodynamics, which is going to be a little bit of the focus of the talk today. As I mentioned, they've really been limited to date. And one of the reasons is that it's just an engineering challenge to create a ground-based, high-temperature, supersonic or hypersonic plasma wind tunnel facility to simulate reentry plasma. The facilities that exist, such as the one here, are also a little bit costly to operate. And when you think about the intersection between interest in taking a risk on a new idea or new development, the cost and the funding that it takes to do that, the expertise that it takes to bring all the disciplines together to do the study, that would probably explain the limited number of simulations. But nonetheless, things have happened. So in Europe, they did MHD interaction study in an ArcJet. So this is work of Guelhan et al. At DLR. And then actually in Australia, and I had a chance to visit this lab at the University of Queensland in Brisbane, there was an Australian Research Council grant to study MHD. And so they used their expansion tunnel facility to simulate MHD forces. And although these results were promising, so in the case of the ArcJet, there was a significant reduction in convective heat flux. And in the case of the expansion tunnel, they did in fact measure enhanced MHD drag, and you can actually see the increase in the shock standoff. These facilities have some drawbacks, however. So the ArcJet is going to have electrodes in direct contact with the plasma, which will basically sputter electrode material into the plasma. And if you care a lot about the plasma electron density and other properties, these minor impurities could actually potentially be the major source of electrons. And then for the expansion tunnel, it's challenging to do the force measurement because you have a test time of on the order of 100 microseconds. So they actually had to develop a novel stress wave force balance to be able to do this. And so, the gap here experimentally is we felt there was a need for a continuous, chemically pure plasma wind tunnel facility that we could operate sustainably for an extended period of time in a university setting. And we also wanted lower pressures, lower chamber pressures than you would typically use for an ArcJet, because we're going to be simulating an altitude that's much higher than peak aerodynamic heating or aerodynamic drag. So our approach for that was to use inductively coupled plasma tunnels. And so that's actually what I started doing in my PhD work and what we're continuing to do here at CU Boulder. And so just to give you a background on what an ICP is, so a inductively coupled plasma torch is something that's used frequently in things like semiconductor manufacturing. So we in aerospace are not really the folks to invent it. But it's a useful tool for aerospace engineering and arc jet replacement because we don't have plasma contact with those electrodes. We are inductively heating that discharge. And because of the way in which we're creating the discharge, we can actually sustainably operate at pretty low pressures. So you can create a RF plasma at a wide range of pressures. And the way that it works is it uses a RF plasma induction coil to artificially ionize and create a ground-based high-temperature supersonic plasma tunnel facility to simulate reentry plasma. And this coil here is energized with an alternating current that has a frequency not of 60 hertz, but of something in the RF range. So a few megahertz. In our case, we have one at 27.12 megahertz, and then another one at a really common frequency for RF plasmas at 13.56. And if I have a time-varying current moving through this coil, I'm going to also introduce a time-varying magnetic field. And if I have a time-varying magnetic field, then through Maxwell's equations, I'm going to have a very strong electric field that's created across this coil. And that's actually what is ionizing that gas. It causes an arc breakdown. Once we have that arc breakdown and we have that ionized gas, we now have basically a transformer system in which the plasma is a secondary in a transformer. And so it's inductively heated to pretty high temperatures. And then we expand that through a converging diverging nozzle to create a supersonic plasma. And that is how the apparatus works. And so this is a 1 kilowatt ICP tunnel from my previous work that's been loaned back to CU and then implemented here. And we say test article is really just a small ceramic sting. We put some ceramic paste at the tip just to simulate some degree of ablation. So the ICP torch is only one component of the system, the systems that you need to have an inductively coupled plasma tunnel. So RF plasma tunnels in general require successful integration of multiple subsystems, much like other high enthalpy wind tunnels. And so you're going to need some type of gas source, moving from the left. In our case, we use argon as a monatomic gas. It's a little bit easier to ionize. It's also inert. So from a facility standpoint, you can exhaust it indoors and it's okay. So on a graduate student budget, that was necessary. And then you're going to need some type of data acquisition and control system. So I chose LabVIEW. I did a lot of analog input outputs, so a few digital input outputs. And then you need the power source. So you need an RF power generator. In this case, I borrowed one from the semiconductor industry. So this is an advanced energy 1,000 watt, 1 kilowatt, 27.1 megahertz RF generator. But in order to actually couple that to the load, you need an impedance matching network. So RF generators output at a specific line impedance, either 50 ohms or 75 ohms by standard. Most of them are 50 ohms. And so we need to make the impedance of the load, which is the plasma, appear to be 50 ohms to the generator. Otherwise, the power will just bounce back. It won't actually be transmitted to the load. So that's what this match network is. It's a system of variable capacitors, and it's actually operated with an automatic control algorithm, and it seeks the minimum reflected power by changing the capacitance. And because we're dealing with AC current, if I change the capacitance, I change the complex impedance of my system, and I can make that appear to be 50 ohms, which is what it does. And that's coupled to this induction coil, which is wrapped around the tube, and then the gas is flowing through the tube. And so the way we actually accelerate the gas is through a rather large mechanical vacuum pumping system, which isn't shown here on this image. And so that's what draws the gas through the tube and actually expands it to supersonic speed. And so the trick is that it's a low density continuous supersonic plasma tunnel. So, obtaining really high densities, generally the approach for that is some type of tank and blow down type operation. In order to achieve continuous operation, we operate at a partial vacuum. And so that's not shown here. And then lastly, you need your test articles. So we have some type of feed through, some type of positioning system, and we have some ports that we can extract signal. We can, input power into the model and things of that nature. So that's an example of a very small plasma tunnel. So what are we doing here at CU Boulder? So our objectives were to establish a larger scale RF plasma tunnel facility in our new Magnetoaerodynamics and Aerospace Plasmas laboratory. And when completed, this will be one of less than 5 such larger ICP facilities in the United States, and one of less than 3, I think, in academia. And so our plan would be to implement a continuous larger scale RF plasma tunnel facility, but with a much larger and more robust test section. So in this case, a vacuum chamber that's water cooled. And the result would be a unique high enthalpy facility, but at lower density, so higher altitudes needed for magnetoaerodynamic study. And so the way that we were going to do that is we're building on a previous experience and work with a tabletop RF plasma tunnel. And we're increasing the RF power level by about 2 orders of magnitude. So from 1 kilowatt all the way up to 40 through 80 kilowatts. We're expanding the test gases beyond argon so we can create air plasma, CO2 plasma. So there's some EH&S things that you have to do when you're doing this at university. So we have a proper external exhaust for hazardous materials. And we're going to couple an inductively coupled plasma torch with a water-cooled stainless steel vacuum chamber and a plasma exhaust system. And in terms of the facility design, I had to make some early choices a couple years ago. And I decided to trade the RF power level with the amount of power and investment that we're going to put towards our vacuum pumps. So the University of Illinois at Urbana-Champaign, I want to say last year, commissioned their 350 kilowatt inductively coupled plasma tunnel, which is the largest such RF plasma tunnel in the United States. And obviously, if you put 350 kilowatts RF power into a power supply, it's going to drive costs and also drive your utility requirements. So what we did is we traded our RF power level. So we have 40 kilowatt generators at a higher frequency with increased mechanical vacuum pump capacity. So instead of 9,200 cubic meters per hour, we can pull 20,000 cubic meters per hour. And we do that through 3 large high vacuum pumps. And this is implemented in 2 phases. So phase 1 is sort of smaller scale tabletop facilities that we've implemented in a separate lab space with the purpose of training students, making sure they know how to operate high voltage. And then phase 2, which is the larger facility. And I'm happy to say that we've actually finished the renovation construction and we've started the equipment now. And so we'll be beginning integration this coming academic year. And so what's shown here is a drawing, but we actually have hardware now, which is really exciting at the bottom. So just to summarize what phase 1 and phase 2 look like. So phase 1 is kind of what we're wrapping up now. Actually, everything in phase 1 is on casters, and in the main lab, when it opens, which is actually soon. We're working in it now, but formally once we've finished our inspections, we'll be able to operate these same facilities within that main lab simultaneously. So it'll be a nice test bed if you want to test something small, relatively low costs, and won't interrupt the operation of the main tunnels. And so these small scale facilities are actually really useful, especially for graduate student research. And there you can test and qualify different diagnostics. You can build small scale models and make sure that it's going to work in the main chamber. The power levels are lower. So if, for example, you have a model that is sensitive to heat, for example, a permanent magnet model, you can test it in a smaller tunnel and not necessarily have it overheat. It's a lot easier to fine-tune control of the power level because things tend to be accurate to some percentage of full-scale output. And so that helps us with that. And then if you want higher enthalpy and higher power, you also have this phase 2 higher power supersonic plasma tunnel. And so the purpose there is a larger scale investigation of aerothermal and plasma interactions. You get a larger test sample size. So depending on the nozzle that you select, you can get a test rhombus that accommodates something like a 1-inch, 2-inch sample. There's a trade there between enthalpy and sample size. We have 2 40 kilowatt, 13.56 megahertz RF generators, and we have 1.5 meter, 2.5 meter long cylindrical vacuum chamber that's water cooled. And we have a vacuum pumping system that is capable of 20,000 cubic meters per hour. And so that results in a Mach range between 3 and 5. We can accommodate stagnation pressures as low as 50 millibars and as high as 3 bars kind of safely if we would like. So where are we with phase 1? Well, phase one is an interim lab that we set up in the building simultaneously while building this other lab. We had utilities in space for two separate tabletop RF plasma tunnels. So one of them at 1 kilowatts, which is my previous torch, and the other one at 2 to 5 kilowatts, which is actually something that my students and I put together new at CU. And so this was actually an effort that they got to lead, which was exciting. And so there on the bottom, you're actually seeing that discharge with a 2 kilowatt RF generator. And if you look closely, you can actually see the Mach diamonds in the jet. And so that's a Mach 3.5 exit nozzle that we're using. Because we're in an interim space, we're limited to inert gases in this interim space, but in the main lab, when we roll everything in, there's an exhaust drop, so you can actually do air plasmas, CO2 plasmas as well. And so right now we do argon and nitrogen just for safety. And then we have an oil-free compressed air supply for air plasmas. We have process-filled water supply in that room, electrical, and two different RF generators. And so if you're interested in learning more about these facilities, there are two different papers that were recently presented at Aviation, one on the development of that new tabletop facility and the other one on some emission spectroscopy done to test the temperature in the jet as well. So phase two is really about kind of scaling things up. So phase two is actually conducted across two rooms. So we have a larger lab space on the first floor. We have a mezzanine area that you see up here. This was actually, it didn't used to exist in this room. We built this as well. And then we have a control room, which is on the floor above, directly above the mezzanine pump room. And that control room is connected to the lab through some conduit we had drilled in the floor. And so this allows us to have a proper external exhaust through the building. So we can do Earth simulations with air plasmas and then Mars and Venus with CO2 plasmas. We're working on the hydrogen. We need a slightly different type of exhaust to meet the fire code, but we're working on it. And so we do have the flammable gas cabinets necessary, though. And so we have approximately 600 square feet of floor space for lab space, 250 square feet of floor space for office space, equipment control, and then the mezzanine space is probably another 300 to 400 square feet. We have a fairly beefy process chilled water heat exchanger that exchanges heat with the building chiller. And so we have an isolated cold water loop in our lab so we can keep track of the conductivity. The building water occasionally has dissolved solids and things of that nature aren't great for RF plasmas. And then we have this equipment platform. So we are actually in an academic building down the hall from several classrooms and actually underneath one of them. And so this was a major design effort to build this equipment platform, have it vibration isolated. So we had to demolish the concrete floor in the room. We had to install footers. It's independently supported on large steel footers. And it's actually not coupled structurally to the building foundation or the classrooms above. It's a steel frame building, so vibration will travel, and it's always important to be a good neighbor to classrooms. So that was a fun design process. And so that's actually what that mezzanine platform looks like. It's got a soundproof door. If you've ever been around some of these larger vacuum pumps, you'll know how loud they are. And basically you can't hear it upstairs, which is nice. And so that's the air compressor on the left. And then we have the 3 vacuum pumps here. And then these are our chambers. So I decided to design the chamber to be modular. And so we actually split these chambers into 2 halves. And so we should be able to operate 2 different 40 kilowatt ICP torches simultaneously. So you could have one with, one test condition, another with a nozzle for a different test condition, which really helps you with throughput. Because again, we're very limited in the number of these facilities that are available in the United States in general. And so these are the 2 40 kilowatt generators pictured here. And then that's the control room that you see upstairs has been completed. So most of the construction is done now. And so now over the last week, actually as recently as July 30th and August 2nd, we commissioned our equipment and turned it on for the first time. And the electrical system holds, so it's 500 kilowatts of total power draw from the building supply, and it kept up with it just fine. So that was exciting. When you kind of start from clean sheet design, which is what we had to do when I started at CU, We started with a room, but we started to work with an architect to figure out what the layout might look like, and therefore kind of spec out our utilities and what modifications we were going to do. So our approach was to kind of start from the requirements. So I knew that we wanted to supply various gases. I knew kind of what our power draw would be, and that drives your chilled water supply requirements. It drives HVAC redesign. I knew the sound levels I wanted to attenuate, which helps us figure out structure, helped us figure out what type of insulation we needed. And so that's kind of what the architectural drawings look like. Um, these rooms were allocated, and we did that design process all of calendar year 2022. We went out to bid in early January 2023, selected a contractor, which it's a public state university, so that took 6 months. We did select a contractor, and we started work in summer of 2023, and so it took about a year for the physical construction. We also had to design this mezzanine space and the control room space. In addition to some of the other equipment up there, we tried to design it so that we could move heavy equipment between the different floors. So there's a davit crane on the mezzanine level. And then we also wanted the ability to create our own secure network between our control room and our equipment for sensitive tests. And so we actually have private conduit that goes between the two rooms. So we'll probably run some fiber to Ethernet converters and run our own network for some of the instrumentation. So this is what it looked like before on the left. So this is the main lab, just an empty room. Thankfully, though, it's already on the main level of the building. And this whole north wing of the building is actually vibration isolated from the other parts of the building where the majority of the classrooms are. So that was nice. And this was the control room. And then this is kind of what it looked like during construction. And so, as I mentioned, we had to demolish the floor partially to the foundation. But while we were down there, we buried a very nice earth grounding rod that we're going to use, because when you have this type of RF current, you need as close to a path to the ground as you can get. You don't want high voltage building up on your surfaces. So that's something that we got a chance to do. And so the contractors did a great job with, I think, a challenging task working in a university building around classroom schedules, but they got it done. And today, this is what it looks like. So same rooms. And so here you can see the new platform, the soundproof doors. We had to really ramp up the HVAC and ventilation in the room. So we did that. The RF generators, and then our new control room. And so we have some wall-mounted displays, and essentially this isn't really going to be a wet lab space, but it's a space in which we can operate our equipment. There's still some things that need to be moved in to the lab that are kind of existing in the hallway, but these pictures are more or less the final spaces. So where are we with our equipment commissioning? So this is actually really recent information. So all high power equipment has been started as of today. And the lab has a capacity for over 600 amps at 480 volt three-phase line voltage. That's what we designed for. We're also lucky in that we're next door to one of the building's main transformer rooms, and so we didn't have to do that long of a wire run. We have 100 SCFM oil-free lab air system that provides basically chemically pure laboratory air for the wind tunnel. As I mentioned, that large pumping system with the three vacuum pumps, and we have two 40 kilowatt 13.56 megahertz RF generators that not only produce power but also enable us to precisely externally control them. We can do things like ramp up and ramp down functions, so that allows us to test different profiles. We can actually program that into the generator, and we can change the power level on the fly. And so, as I mentioned, all major equipment has been commissioned, and we use this resistive water-cooled load to test each generator at full output power, and checked for RF safety, and have done those checks as of today. So, what's left? Well, what's left is integration. So, phase 2 integration will be starting to occur in fall 2024. And essentially, we have the parts necessary for our new plasma torch, but we haven't actually had a chance to assemble it. We've moved those two large chambers into the lab. Oops, sorry. And we actually have to manifold those vacuum chambers together. So that's the design for the manifold. So that was something that we designed. It's already been manufactured. It's actually supposed to ship this week from the East Coast and Pennsylvania. And that's all coupled to a control panel. And what's nice about this system is that we are actually able to externally control the chamber base pressure. So as I mentioned, these MHD effects, they're altitude dependent. And so we have the ability from the control room to set the chamber pressure to something between 1 and 100 torr. And this system will either actuate the valves to shut off one or several of the pumps, and then also bleed air into the manifold, but downstream of the test so it doesn't go back into the chamber, so that we're effectively changing the nozzle exit pressure and therefore the simulated altitude. And so that work is ongoing. The stainless steel chamber is one aspect of it. So we have these viewports in the front, but we also have a conical diffuser inside of the chamber that we're designing. The adapters necessary to do that. So you need different vacuum adapters. You need water-cooled baffles. Those things have been designed, purchased, they're on site now. So we have to actually install them, which is going to be a fun task for the students to do, and myself. And then this is an example of one of those water-cooled baffles that exists in line in the plasma exhaust. So these things are basically a heat exchanger. So you've got some vanes that are cooled by cooling water, and if you want to get aggressive with it, you could use LN2, although our cooling water is sufficient in our testing. And although we're in partial vacuum, you get decent convective heat transfer with these because we're actually at a relatively high pressure for what folks consider vacuum. And so we're at a few hundred millitorr or maybe a couple of torr, which is enough for the flow to be considered a continuum and not in the free molecular regime. So you do actually get some cooling through these baffles. We also, through our diffuser system, try to slow the flow down as close to Mach 1 as we can. And then if there's a shock wave before these baffles, we hope it'll be a weak shock wave, and then that also helps us with our heat transfer. It's really important to cool this flow before it gets to the vacuum pumps because it can destroy the pumps if it's too warm. So just a kind of summary of our capabilities. So just to put some numbers to it. So here are the specs for the 1 kilowatt tunnel. As I mentioned, it runs on argon and nitrogen right now. It can do air plasma. I have done an air plasma in it. It's just we don't have the right exhaust. So we're going from 0 to 15 standard liters per minute here in terms of the gas flow, mass flow rate. Operating power 0 to 1 kilowatt. And the test section is only a small 1.5 inch diameter tube. Downstream pressure is less than 20 torr. So this is all partial vacuum. And the Mach number ranges from 0 to 3.5. For the 2 to 5 kilowatt tunnel, now we're increasing the gas flow rate up to 50 SLM. We operate from 0 to 5 kilowatts, and we've seen temperatures in the range of 1,000 to 3,000 Kelvin. And now we have a 12-inch by 12-inch vacuum chamber with modular feed-throughs, so now we can insert models in the flow a lot easier. We have nice optical access, so we were able to do some emission spectroscopy and thermocouple measurements just as a preliminary test case. So how does that compare to the larger facility? So these are sort of our estimated parameters. We have a pretty good idea of what our mass flow rates will be, mostly because we bought our mass flow controllers. Thanks. And so that's 0 to 500 SLPM, standard liters per minute. Operating power, I say 0, we probably have a minimum operating power of about 0.5 kilowatts, just because when you use RF generator this large, it's only regulated within plus or minus 400 watts. And then our test section size is a 1.5 meter diameter. The inner diameter of this chamber is about 48 inches, 49 inches, flange to flange. Downstream pressure can be as low as less than 1 torr because of the relatively powerful vacuum pump system. And the gas temperature gets bumped up to 5,000 to 10,000 Kelvin. So it's quite warm. And also because of the enhanced pumping speed, we can reliably do higher Mach numbers if we choose to install such a nozzle, so up to 5 continuous. And so that's kind of a summary of our facilities. In terms of where we exist on the map, so one of my students kind of helped adapt a map from a previous study that didn't have some of the tunnels, so we updated it. So these are a map of not only ICP facilities, but also ArcJet facilities and hypervelocity facilities like blowdown tunnels around the United States. Of course, there's one here at Langley. There's the Arnold Engineering Research and Development Center, ArcJet type facilities in Tennessee, and then ArcJet at UT Arlington. UIUC has another large plasma tunnel, the University of Vermont, and then now C. Boulder as well. And so just to kind of summarize where we are. So recently, work in MHC and hypersonics has actually been ongoing in Europe and the United States. And Europe, in this respect, is perhaps, if not necessarily ahead in terms of the history, but maybe in terms of integration. They've actually stood up this program called Magnetoaerodynamic Enhanced Entry System for Space Transportation, or MAEST. And it's sort of a consortium of universities and government entities that are actually driving this technology forward with high temperature superconductors, but also modeling, so computational modeling infrastructure and experimental infrastructure as well at the various plasma tunnel facilities in Europe. In the United States, there's been numerical and experimental work in government and academia. So this image is actually from NASA Langley's hypersonics and MHD concept, which has been licensable technology from Langley since 2023. It's actually been in development, of course, for a lot longer than that here at Langley. So this is an example of some of our recent research activities. So we do and have been busy with a lot more than the construction. So of course, the construction I've been mostly taking the lead on, try to insulate my students from it so that they can make academic progress on their degrees. And then we have the interim tabletop facilities, and each of the students, they all work together on these, but of course, each of them specialize a little bit. And we've also been doing some systems design work. So one student in particular, his name is Danny Wen, has been coming to Langley on numerous occasions for various internships, working on looking at incorporating reduced order models for MHD into tools such as POST for error capture studies. We've also been doing some work with Sandia in the past. So we've been designing a novel RF and microwave instrumentation suite that would actually measure the signal attenuation through these plasmas and then try to back out essentially what the plasma properties are, which could be a nice way to diagnose what's going on with the plasma during flight, for example. So these are the students in the lab. As I mentioned, they make a lot of the lab go, and standing next to the discharge that they help create, this 2 to 5 kilowatt torch. And so I have individual slides on that kind of summarize their work, but after this, but I just wanted to pause here, and I'll take any questions you have. So thank you.
All right, if there's a question in the room, use a mic. If there's a question online, raise your hand. Yeah, Mike. Should be green. Hit the button at the end.
Hey, Hisham. Great to see you again. Great presentation. Had a question about what you'll be able to test in terms of your facility. As you know, from Mars, we have to deal with Hall effects and ion slip, and that causes the spacecraft to spin and possibly even tumble. Are you going to be able to simulate that and also develop some flight control strategies with your facility for being able to land really large stuff at Mars?
Yeah, it's a great question. So yes, our plan is to effectively control for that effect by varying the pressure during a test. So, for example, in a CO2 plasma or even with argon, if we can vary the pressure, we're basically varying the collision rate, and we can therefore vary the impact of the Hall effect. And so that would be a really interesting study. In terms of control strategies, one of the things that we're working on right now, and one of the reasons we design our own tunnel, is the ability to incorporate force balances in these plasma jet facilities, which is sort of a novel thing. Force balances are common in electric propulsion testing, but not necessarily always in ArcJet testing. And so that's actually what we are looking at doing. And so we have a strain gauge based force balance that we've insulated from the flow that we're actually in the process of testing. So you can imagine with an electromagnet, you can potentially measure what these MHC forces are as a function of magnetic field. And then you could then, using computational tools, figure out what your control authority might be. So that's one of the objectives. So actually, Danny is taking the lead on that. So he's transitioning from his work on POST. And now that he's wrapped up the first contribution of his PhD, he's been over the last year working with some existing MHD test articles that I've had. And he's been the one building the force balance. And I saw it in the lab the other day. They have some calibration weights on it. So it's going well. Yeah. So.
I've got a logistics one. How much does that all cost, and who's paying for it?
That's the $1 million question, right? It is expensive. So we have invested a few $1 million at the University of Colorado, and that money has come from the University of Colorado primarily, from startup, and for the construction at least. And then in terms of the equipment, that's something that I'm funding as well from that. We've had some student fellowships that help pay for some of the students. So we have some NASA fellows, 2 NST-GERO fellows as of this fall, some NSF fellows. But yeah, it's a pretty resource intensive project. And so, I'm just, in terms of the funding, it was something where Colorado, I think, saw really the value add. And I knew there was a need, and you put together a proposal, and it was something that was chosen. So, yeah.
There's one online here. How accessible are these systems for use?
Pretty accessible. I think one of the reasons that I decided to split the chamber into 2 was to increase testing throughput. So we have one external testing customer, the local aerospace company in Colorado, that wants to test some non-ablating TPS materials, but we can do ablation as well. And so that's something that we are setting up the infrastructure for right now. And we're hoping that integration will go well in fall of 2024, and we'll have plasma by the end of the year. Of course, after that, there's a kind of characterization effort. I didn't have a chance to talk a lot about the different sensors and diagnostics we'd have. And so those are going to be things that we'll probably offer in 2025 and beyond. And so our first scheduled test, I think, is next summer. Yeah, for an external party. Yeah.
All right, there's another one. Is your chamber able to perform atomic oxygen tests?
Technically, yes. There's nothing that prevents us from doing so. One of the things that we did with our vacuum pumping system, you have to make an early design trade in terms of your percent oxygen concentration. We went with hydrocarbon-based oil because it's a better lubricant. But it does mean that if you flow pure oxygen into your chamber, you need to dilute it. And so with our purge gas system, we have the ability to flow pure nitrogen into the purge gas system. So it's possible. It's just a cost associated with the nitrogen, but it's a pretty small flow rate. It's like 3 CFM or something like that. So, yeah.
Any more?
For your facility, and you talked about controls, do you have the ability do you foresee being able to have the ability to put multiple magnets, electromagnets in there at the same time to look at differential control and the kind of like cross pollination of those magnetic systems in the flow?
Yes. Yeah. I mean, one of the reasons that the chamber is designed the way that it is, and let me see if I can find a good picture of it, is to have multiple feed throughs. So ports on a chamber kind of help drive the cost, but we felt it was worth it. So we have on each side 7, conflat 2 3/4 ports, and they're arranged. The chamber is actually symmetric as well, which is what let us split it to 2. And so those feed throughs, you can feed through power through those. You can feed through water cooling, and so there are different zones that you would use for different things. But yes, you can feed through power to multiple electromagnets. Of course, when you start doing that, the test gets more complicated. You need more power supplies, but it's in theory possible. Yes. Yeah.
All right. I think that one more, last one. Okay. You mentioned convective convective heat flux reduction behind the shock. What about radiative heat flux?
So that's actually something that we're looking to test experimentally. We've seen in previous studies where folks have done MAC interaction that the magnetic field changes the optical thickness of the shock layer and thereby the radiative heat flux. It also drives some enhanced ionization in the free stream as well. That's been noticed. So it could potentially increase it. And so that's something that we're looking to look at experimentally. In terms of the convective heat flux characterization, we have a slug calorimeter on site, and we're going to be sweeping that through the flow. And so we'll be trying to get the heat flux as a function of distance from the nozzle, and also, to assess the uniformity for like a radial profile. So,
All right, let's thank our speaker one more time.